let's get going. So let's prove this theorem that I didn't prove last time. So suppose we have, this is a theorem, a circular line C and Mobius transform T, then points Z and Z star are symmetric with respect to C if and only if are symmetric with respect to T of C. Okay, so in other words, Mobius transforms preserve whatever symmetry you see. So if you have some line or circle and a couple of points Z and Z star, which are symmetrical, then when you think of Mobius transforms as just being a kind of a rearrangement of the complex world. It's a bijective holomorphic mapping. It's rearranging the complex world, and you're turning potentially your line or circle into either a line or a circle. Let's say, for example, it's now a line, and the symmetry relation you get is preserved. So whatever symmetries there are in your original world, after you transform it with your Mobius transform, even though lines can be circles and circles can be lines, or lines can be different lines, whatever rearrangement of the world you have, the symmetry relations preserve, which is a pretty extraordinary thing, but that's this subject is full of extraordinary things. So this is C and this is T of C. Okay, so this is going to follow from using cross ratios. In a kind of a clever way. Okay. So, proof. We're going to start with the first case. Suppose that the image of our line and circle is equal to R. Yeah? Now, notice since we have that 0, 1, and infinity, these are all points on R, and T is a invertible mapping, right? So there exists Z1 and Z2 and Z3 such that T of Z1 equals 0, T of Z2 is equal to 1, and T of Z3 equals infinity, right? Because T is invertible, we just take the inverse of T on 0, 1, infinity and get these points, Z1, Z2, Z3. Okay, so that's definitely true, yeah? But if we define T tilde of Z to be this cross ratio, or this Mobius mapping we get from the cross ratio, right? So if this is how we define T tilde, then obviously T tilde does the same thing, right? Because that's the basic property we use several times. So if we consider, for example, the mapping, say T, so T tilde to the -1 of Z, what does it do? Well, then if we act on 0, 1, and infinity, they just send them to 0, 1, and infinity. Oops. Right? Because t to the -1 of 0 is z1, and then t of z1 is 0, right? Yeah? So this Mobius transform of t composed with t tilde, the inverse, yeah, is fixing 3 distinct points. Yeah? And we already saw the last time that there was at most 2 fixed points of a Mobius transform. Right? And the only way that you can have 3 fixed points is if this Mobius transform is the identity. Yeah? So fixes 3 points and must be identity. And if you remember the proof, it was just, we wrote down the consequences of having t of z, let's call it something else, s of z equals s. If we write down the consequence of this, it just turns out to be a quadratic, right? You just do the algebra, right? And you have at most 2 distinct solutions to the quadratic. Yeah? So in any way this can be the case, if you have 3 distinct things that are fixing it, is if you have a constant. So it fixes 3 points, and so t composed with t to the minus t tilde to the -1 is the identity. In other words, these things are the same mapping. T equals t tilde. Yeah? Cool. And what we learned last time is that symmetry symmetry in the sense that we normally understand it, symmetry across a circle in the sense we discussed, or symmetry across a line, is equivalent to symmetry in the sense of defining it with respect to this cross product. So with respect to this Mobius transform defined by the cross product. So we know that Z and Z star are symmetric with respect to C if and only if, when we do this thing, T of Z T of Z bar equals T of Z star, like this, right? That's what we learned the last time, yeah? Yeah, because this is exactly this cross product thing, right? Because this is the same as Z, Z1, Z2, Z3 bar, and this thing is the same as Z star, Z1, Z2, Z3, right? This is exactly what we learned last time, yeah? Give me a thumbs up if that makes sense to you, yeah? Cool. All right, so these guys, symmetric exactly implies this, yeah? Yeah? But this thing is exactly the statement that images are symmetric across T of C, huh? And this is exactly saying that T of Z and T of Z star are symmetric across T of C, because T of C is just R. Yeah? Because if we have R, then T of Z and T of Z star being symmetric is exactly this statement right here. Yeah? This is exactly the statement that these 2 points are symmetric across R. With me? Thumbs up if you're okay. Sanka, you okay? Because look, this is R, right? So this is some number a plus ib, right? And this number a plus ib is symmetric across R if and only if this thing is a minus ib, right? So this picture is exactly the same as saying that a plus ib complex conjugate equals a minus ib. Yeah? Sanka, you okay? Okay, cool. All right, so in the case when the image is the real numbers, then this thing is trivial. This thing, not trivial, but this thing follows from what we know already about symmetry being equivalent to this condition for any 3 points. Yeah? Cool. All right, so if we instead start with a real line, so if C is the real line, then consider or define S to be equal to T to the minus 1. Yeah? And let's call this thing T of C. Now this thing doesn't have to be a real line anymore, but it is a line or a circle. And then S sends this guy onto the real line. Yeah? So let me see if I can put everything on the same page. So if we have that C is this thing, right? And if Z and Z star are symmetrical with respect to C, which is R, yeah, then this is equivalent to saying that Z bar is equal to this thing, like this. Yeah, that's exactly symmetry across R. And let W equal T of Z and W star equal T of Z star. Yeah, so S of W equals Z and S of W star equals this thing. Yeah, and now we have S is a Mobius mapping from some line or circle S tilde into R, right? And by what the case we've just established, we have that, so we know that Z and Z star are symmetric. Sorry, let's do this. W star, W star are symmetric with respect to C tilde if and only if S of W, S of W star symmetric with respect to S of S tilde, which is equal to R, right? But this statement is exactly the statement that Z and Z star are symmetric with respect to the real numbers, right? So let's see what we've established. Oops, like this. So what we, and this is exactly the same as saying that Z and Z star symmetric with respect to C. So in the case that we have C is the real numbers, yeah, then Z and Z star symmetric with respect to C, yeah, is exactly the same as Z bar being Z star, yeah, which is exactly the same as saying that the images are symmetric, which is true if and only if W and W star is symmetric across C tilde, which is true if and only if T of Z star and T of Z are symmetric across the image. Yeah? So putting all these things together, this is the same as saying that T of Z and T of Z star symmetric with respect to T of C. Cool. All right, so if either the image, the real line, or if either our starting line or circle is the real line, or the image of our circle or line is the real line, then this thing is true. Yeah? Either of those things is the case, then this thing is true. So what we have to do now is the fully general case where we have that neither initial C or the image of C is the real line. Okay, so if C is not equal to the real line and T of C is not equal to the real line, then we have the most general situations. Let's draw a picture. So we have C could be this circle like this, and T of C could be another circle like this, say. Neither of these look really like a circle, but okay. And let's draw the real line like this. Yeah. So T is doing this, like this. Yeah. Cool. So the idea of the proof is we are going to use what we know about the case when we are mapping onto the real line, and then factor the general mapping T through it. So we're going to do this in the following way. We're going to create a mapping that goes from C onto the real line. Let's call that S, like this, which we can do using our cross product. Okay, using the Mobius transform we get from the cross product, and then we're going to go back from the real line through C down to T of C by composing what we have by going from S to the -1 from the real line back to C and then composing with T. And we're going to call that mapping Q. So I'm going to say Q of Z is going to be T of S to the -1 of Z, right? So Q is going to send the real numbers into T of C, like this. Yeah? And S is going to send C into the real numbers. And the way we've set this up is that we have our mapping that we're actually interested in T. T is what happens when we map with S and then map back with Q, right? So we're going to have T of Z is equal to Q of S of Z, like this. Just by the way this thing is defined. If you just stick S of Z into this, you get T of Z. Yeah? But the point of all of this is that every time we compose a Mobius transform, we get a Mobius transform. So the good symmetry properties we have in the case when we are mapping either from or to the real numbers are true. So our guys here, Q and S, will satisfy the symmetry properties that we like. Yeah? And that'll allow us to prove the symmetry properties with respect to the general mapping by just sort of filtering it through these intermediate mappings that we've created. Okay, that's how this is going to work. So first, let's just create the mapping S, because once we have S, then Q is entirely defined. So define we're going to use the Mobius we create out of this cross product. So I'm going to find it, like this. For some choice of Z1, Z2, Z3, which we pick on C. Okay, then what are we going to do? So if Z and Z star are symmetric with respect to C, then what this is equivalent to, that when we first map it with our S, so S of Z, S of Z star, are symmetric with respect to R, right? Yeah, that's a true thing, yeah? And if we look at this mapping Q, right, since S and S star are symmetric with respect to R, if we map this with Q, then the images of S and S of Z star, start again, images of S of Z and S of Z star have to be symmetric with respect to T of C, because Q is mapping from R to T of C, and that's the case where we've already established the symmetry is true. Yeah? So this is equivalent to Q of S of Z and Q of S of Z star are symmetric with respect to T of C. And by definition, this is just T of Z, and this thing is just T of Z star, right? So we have exactly the statement that we want. Yeah, we have exactly the statement that we want. Cool. So the general case is kind of easy, reduced down to the special case through this factorization. All right, cool. So now we have this. I want to do another example of calculating Mobius maps, because this isn't a particularly easy topic. It's just not a particularly easy topic. It gets rapidly easier the more you do them, but yeah, when you initially start to do this, if you haven't done them before, these things can be tricky. It's also kind of just extraordinary every time I do these examples that, as I said before, that these things exist. That if I was working on a research problem and I proved that some function has these properties, that it obeys this symmetry property, that it preserves angles, then I'd think, okay, great. Then the only thing that can possibly be is a rotation or dilation, and I'd be really happy that I've shown that that I was very close to solving some problem, because I think nothing can possibly satisfy all these conditions unless it was just an affine mapping. And it turns out that that's completely false. So it kind of shows you how these, I don't want to say monsters because these are very nice mappings, but how you think that something's incredibly restrictive, you have very restrictive properties, and it still turns out that there are many examples of them there. There can be more flexibility. There's more possibilities in the world of math than a priori you might expect. All right, so this is our example. So we're going to take this mapping. And we want to find the image of L of C, which is the imaginary line. So it's this thing. It's the set of C plus IY I belong to R. So it's the imaginary line that goes for the real number C. Right? So this is 0. I'm going to need a bigger picture than this, but okay. This is C. So it's the image of this thing. So solution. All right, so let's start to try and figure this out. Well, let's look at our initial mapping. Do you think that the image of this line will be either a line or a circle? What do you think? Well, that's a stupid question. Of course, it's a line or a circle. Which is it, a line or a circle? Mm-hmm. Yeah, exactly right. So if C is not equal to 1, then f of L of C is a circle, otherwise a line. Okay, so let's try and figure out the elementary properties of this. So I should have put this on the left-hand side, but okay. This is where we're starting from, and we're mapping it with mapping, we'll call it F, right? And let's consider the case when it's not equal to 1, because this is the harder case to begin with. So take C not equal to 1. It's got to be a circle, right? So when you're doing this homework problems, a really good idea is to take colored pens and to draw stuff in the domain and then draw stuff in the image that you know it's being sent to. Okay, so we know that this thing is going to be sent to some sort of a circle, and that's all we know at the moment. But we want to begin by exploiting the fact we have angle preservation. So we see that this line is perpendicular to the real line. So let's think about what happens to the real line. See if we can understand that. So if we look at this thing applied to the real line, well, there's a couple things we can do. So want to find f for the real line, because that's going to be easier than our general line L of C, right? And what do we notice? Well, we notice that f of 1 is infinity, as already pointed out. F of 0 is just going to be -1, right? And what else? And f of infinity is just equal to 1. So 1, 0, and infinity all belong to the real line, and these are all points on the real line, so the real line must be sent to the real line. Yeah? Yeah? We know the real line will be a line because it does go through 1 itself, right? And the line that we have goes through infinity, -1 and 1. In fact, just knowing -1 and 1 would be enough. So we know that the real line is mapped to the real line. So let's make this thing blue. I don't know how well you can see that. So let's put little circles here. And we know that this thing is being mapped to this thing, like this. Yeah? Cool. All right. Then what else do we know? Well, let's think about the intersection points between this line L of C and the real line. Well, they intersect at C, right? Yeah. And they also intersect at infinity. Yeah, they also intersect at infinity. So we have that the image of L of C is some sort of circle that intersects this thing in a perpendicular way at 2 points, right? One of which will be the image of infinity, and one of which will be the image of C. Yeah. So f of L of C intersects the real line at f of C and f of infinity. And what is f of C? Well, it's some complicated expression. Let's keep it like this. And what is f of infinity? F of infinity is just 1. Right? And we also know that f of C is f of C is a real number, but we know that the circle has to have its center on the real line, because if it didn't, then there's no way that the angles which it crosses can be perpendicular. Yeah. So it has to be something that has its center on the real line, and we know that the circle is intersecting this line at these 2 points. So f of C is just some real number. So it's C plus 1, C minus 1, whatever that is. So it depends on whether or not C is bigger or less than 1, right? But just to put something somewhere, let's just put this thing here. Yeah, let's put this thing here. So this is 0. So let's say this is f of C, and this here is 1. And it could be that f of C is on the other side of 1. We don't know yet. We're going to figure that out. But they're both on the real line. And what the circle has to do is it has to intersect these two things. So the circle has to go like this. The circle has to go like this. Yeah. So this thing has to be f of L of C. Okay, and that gives us a lot of information. I mean, so we know explicitly what this point f of C is, right? So we could find the diameter of this circle and therefore its radius, yeah? Just explicitly from this. But then we sort of have an ambiguity of whether or not it's on this side of 1 or the other side of 1. So we have to figure that thing out. Okay, so we have this mapping. F of Z is equal to Z plus 1 over Z minus 1. And line we are considering the image of is L of C, which is this thing. It's the set of C plus IY for any Y belonging to this thing, right? And we've seen that f of the real numbers are the real numbers. And so if C is not equal to 1, then L of C is a circle, or f of L of C is a circle. Right? So let's draw a picture. So this is 1, and let's take C to be less than 1. Just put the line somewhere. This is L of C, and we are mapping it to a circle, and here, this is 0, because when we put infinity, then f of infinity is 1, so we are going through this, which is f of infinity, and we're also going through f of C, wherever that is, right? So just to put something, let's suppose f of C is here, and the circle we have does this, and because f of C is explicitly calculatable, we can find out the diameter of this circle and therefore the radius. So all we need to know is if the center is on the left or the right hand side of 1. And actually we can just consider this quantity And then we have C plus 1 over C minus 1, and then minus, let's write this 1 as C minus 1 over C minus 1. And then we're going to have this cancellation. We're going to have this 2 over C minus 1, which is pretty convenient because then it says that if C is less than 1, then this quantity is negative, right? And therefore we are on the left-hand side, right? So of 1, so f of C is equal to 1 plus 2 over C minus 1. So we are to the left of 1 if C is less than 1, which is as this picture shows, and we are to the right of 1 if C is bigger than 1. All right. And the center of the circle is on the same side of 1 as f of C is, right? So this gives us the following good stuff. So we know that the diameter of the circle is, whether we're on the left or the right-hand side, the diameter of the circle is given by the absolute value of f of C minus 1, right? Which is just going to be 2 over the absolute value of C minus 1, whatever value of C is. Yeah? And the center of the circle is going to be half of this quantity, either plus or minus half of this quantity, depending on the sign, right? So, and the sign is actually encoded in the expression itself, right? So if C is less than 1, then we're on the left-hand side, and this is properly negative. So the center will be 1 plus 1 over C minus 1. Because if C is less than 1, then from this calculation, we know that f of C is to the left of 1, right? So we have to, and we know that we are moving by half of this quantity to the left of 1, which is exactly this, right? And if C is bigger than 1, then we are to the right of 1, right? So we are moving half of this thing, yeah? And if C is bigger than 1, it's still this expression. So the center, whether C is bigger or less than 1, is always this thing, yeah? So center and radius is exactly half of this thing, is 1 over, let's see, it's 1. So finally we can write that f of L of C is the ball of radius 1 over C minus 1, absolute value of 1 plus 1 over C minus 1, if C is not equal to 1. And this makes sense, right? Because, well, it makes sense because when we compare it to what happens when C is actually equal to 1, so if C is equal to 1, then this line goes through the 1, and therefore we are sending a line to a line. Then f of L of C is a line. It's a line that remains perpendicular to the real line, right? And it goes through 1. So line perpendicular and 1 belongs to L of. So that's pretty easy. Then it just has to be this thing, this line that goes like this. Right? Not a very good line. So what we see is that as C gets closer and closer to 1, this ball is tending closer and closer to this line, because as C gets closer and closer to 1, less than 1, then the radius is blowing up and the center of the circle is blowing up. So we are actually having a circle which has got center like way out here, and it looks more and more like this, right? So as C gets closer and closer to 1 from the left-hand side, then the image of this line is this larger and larger and larger circle whose centers more and more off towards minus infinity. Yeah? And if C is more and more close to negative infinity, then the circle is getting smaller and smaller and smaller in its radius, and it's getting closer and closer to 1. So circles with very, very big or very, very negative C are doing this. Right? And if C is bigger than 1, if it's close to positive infinity, again we have a circle which is kind of looking like this, where its center is way off like this. And if C is just a little bit bigger than 1, then we have, sorry, did I say this wrong around? I said this wrong around. Say this better. Say this correctly. So if C is just a little bit bigger than 1, but is bigger than 1, yeah, then this is a huge number, and so is this. So the radius is this huge radius with the center way out here, and looks more and more like the flat line, as we expect, because as C approaches 1, we expect it to converge to the shape we get when C is actually equal to 1, right? Or to the line or circle we get when C equals 1. And when C is going towards positive infinity, then this is a very small number, so it's a circle almost centered around 1, just a little bit to the right of 1 with a very small diameter. So this is what it looks like. Right? So as C gets closer and closer to positive infinity, we get these smaller and smaller circles. And all of the circles, no matter what, always touch 1. So that is what this Mobius transformation does. And yeah, it turned out that we didn't need to use symmetry properties to figure out which way, which side of 1. We just needed to explicitly look at this. Another thing we could have done was just a case-by-case analysis of what happens to this expression if C is bigger than 1 or C is less than 1. Yet another thing we could have done is just take the derivative of this expression, because the derivative is either going to be positive or negative, because it's a Mobius transform, so it's invertible, and it's setting the real line to the real line. So it's setting the real line to the real line in an invertible way, which means that as we go from left to right, then the image has to go from, well, the image has to be either increasing or decreasing. We can hit infinity at a finite point as we do, but we are always either going to be increasing or decreasing, because we can't double back on ourselves, right? Because then it wouldn't be a one-to-one mapping. And sure enough, if we do calculate the derivative of this thing, then it's turns out to be, just differentiate the top guy, leave everything on the bottom guy squared, x minus 1 squared, differentiate the top guy of 1. So we're just going to have 1 and minus 1, so it's just going to be minus 2 like this, right? So it's the derivative is negative, so this function acting on the real numbers will be decreasing, and that too makes sense, right? Because as we have this vertical asymptote at 1, so we are at positive infinity just a bit bigger than 1. So we like try and graph this. Then if this is 1, then we're going down like this. Yeah, like this, with our decreasing function. And we have a vertical asymptote like this. Yeah. Yeah, and as x tends to minus infinity, this is going to tend more to 1. So, right, it's going to cross at minus 1, so it's going to be some sort of function like this. So this is what this function looks like in the real line. So it's a decreasing function for every x. Yeah, and yeah, so that's another way we can tell that for C, which is bigger than 1, then f of c is bigger than 1. And for c which is less than 1, then f of c is less than 1. Okay, let's talk about automorphisms of the disk. So, automorphisms of any set. So, given open mapping, open set. We're going to write odd of omega is a set of holomorphic mappings that map omega to itself. So f from omega to omega bijective holomorphic. Okay, so let's take the simplest case. So if omega is equal to d, then it turns out that we can find a large class of these examples in the following way. So let's define this thing equals alpha minus z. Over 1 minus alpha bar z. Okay, firstly, let's reassure ourselves this is actually holomorphic on the disk. So let's take a look. Take a disk like this, where alpha belongs to the actual disk. So if alpha belongs to the disk like this, then if we take the reflection of alpha through, then we know it's equal to like this thing, it's on the other side, right? So the only way that this thing becomes 0 is if z is equal to 1 over alpha bar. But 1 over alpha bar is well out from outside of the circle, so this thing is indeed holomorphic inside the disk. Yeah? And so holo in the disk, and it's also going to map the unit disk's boundary onto the boundary itself. So notice the following thing. So let's do this. So if z belongs to the boundary of the disk, then this thing is because z has got length 1, right? So z bar has got length 1, so 1 over something of length 1 is just 1, like this. And then what is this? This is just alpha minus z over, and let's just multiply this through. Z bar minus alpha bar, and then this is just z times z bar, which has just got length 1, like this, right? Like this, yeah. And then what's this? This is alpha minus z over z minus alpha bar, like this. And then this is just 1, right? Because the top is just bar times the bottom, right? So clearly 1. So we are mapping the boundary into the boundary, right? So let's write the conclusion of this. So by the maximum principle, we have that this guy has to actually be contained inside the disk itself, right? Because the maximum of of phi of alpha of z for anything inside the D has to achieve in the boundary, and the maximum is going to be of length 1, right? So we definitely map inside the disk itself. Yeah? Cool. So now we just need to show that this is a bijection, that it maps itself to itself. Yeah? And what's curious about this thing is that when it composes with itself, it actually inverts itself. It's a self-inverse. So to see this, note the following. If we consider phi alpha of alpha, this is equal to 0, right? And phi alpha of 0 is just equal to alpha, like this. Yeah? So this is therefore saying that if we consider phi alpha of 0, this is phi alpha of alpha, which is equal to 0. So this thing is fixing 0, right? And then phi alpha of alpha is equal to, using this, it's equal to phi alpha of 0, which is equal to alpha like this. So it's also fixing alpha. Yeah? So phi alpha composed with phi alpha. This is a perfectly well-defined holomorphic mapping, right? Because we know that phi alpha is mapping into the disk, so then we can compose again with it, right? So this is a well-defined holomorphic mapping, yeah? Is holo on unit disk, yeah, and is less than or equal to 1 on the unit disk, right? And it is fixing 0, right? Yeah. So when have we seen mappings like this that have these kind of properties? When have we seen mappings that have these kind of properties? What result do we have that talks about holomorphic mappings from the unit disk where the absolute value of them is less than 1, right? Where we have them fixing 0. So if f of z, well, and what cool things did we have for such mappings? So, okay, hint. So if we took the Taylor series of this, right, f of z, then the first term would be 0, right? So then we'd have k equals 1 to infinity ak z to the k, you know, which would allow us to do this and have a holomorphic mapping itself, right? Yeah. And by the maximum principle, since as we are near the boundary of the disk, this thing is going to be more or less than 1, a little bit bigger than 1, but close to less than 1, then we could show that this is true, right, for all z. inside the disk, right? Yeah? And what is this? This is Schwarz's lemma, right? This is Schwarz's lemma. Yeah? So from these hypotheses, like this, from these hypotheses, we can conclude that this is true. Right? For all z. Yeah? And if we have a case of equality, then what does that mean? If we have some z inside the disk where this is an equality, what does it mean? Yeah, and alpha is going to just be a complex number of length 1, right? If we have equality, then it has to be alpha. It's got absolute value 1, right? So it's just going to be a rotation if we have equality. Or if we have that f prime of 0 is equal to 1 by the similar argument. Yeah? So this is Schwarz. And we're in a position to apply Schwarz here because we have a holomorphic mapping. It's mapping inside the disk, right? This is mapping inside the disk, yeah? And it's fixing 0. Yeah? Yeah? But we have even more. We have that it's also fixing another number. Yeah? And therefore we have a case of equality in this thing, i.e. that's true. Huh? That's true. Yeah? So this implies that phi of alpha composed with phi of alpha of z is equal to some complex number, let's call it beta now because we used alpha of z, with absolute value of beta is equal to 1. But then this is only possible if this beta is actually just equal to 1. So let's call this thing star. So, but so it's not double, it's not reciprocal, this is one-way direction. So this is Schwarz. But by star, we have that beta can only be 1 because this is just not true unless it's just be equal to 1, right? See what I mean? So we have beta is equal to 1, and therefore this thing, whoops, where is it? There we go. So phi of alpha composed with phi of alpha of z is just z. In other words, phi is an inverse to itself. Yeah? So phi alpha to the minus 1 is equal to, well, phi has an alpha and it's given by, phi alpha has an inverse and it's given by itself. Yeah? And therefore we have that the function is now an automorphism of the disk to itself. Yeah? Oops, itself. Cool. So we have an explicit collection of examples of automorphism from the disk to itself. And what is striking and kind of unusual is that after multiplying by just a rotation, a complex number of length 1, these are all the examples. So every other example is something like this times a complex number of length 1. Right? So there's a very specific class of functions for which this is true. So, theorem. Every automorphism, I don't know if let's call it an automorphism. It's definitely not spelled like this, right? Every automorphism of D to itself is of the form e to the I theta z minus alpha over 1 minus alpha bar z. The sum theta belonging to minus pi to pi and alpha inside the disk. So we can have a rather specific characterization of what these guys are. We know really quite precisely what these guys are, right? And as a consequence, the only automorphism that fixes 0 has to just be a rotation, right? So consequently, if phi belongs to automorphism group of this thing, then and phi of 0 equals 0, well, since it has to be of this form, if when we put 0 into this we get 0, then that means that alpha has to equal 0, right? So then this entire thing is just a rotation. Mm-hmm. Then phi is a rotation. Okay, and you notice I use the word group because this is a group, because we can simply take any two automorphisms and compose them and have another automorphism. Yeah? And we have a notion of an inverse automorphism, right? An inverse group element, which is the inverse automorphism. And we have the identity, which is just the automorphism which sends Z to Z. Yeah? So this thing is actually a group, right? And this thing rather explicitly says what nature, what formula they have. But let's take this further. So recall we have that this mapping, call it F, which was defined by this. This sends the upper half plane into the unit disk, right? This is the first Mobius mapping we studied, right? So this thing is an invertible automorphism of the complex plane, right? Mobius mappings are automorphisms of the entire complex plane, yeah? And that means that with this guy, this invertible mapping from the half plane to the disk, if we have an automorphism of the disk, we can turn it into an automorphism of the half plane by mapping it back with f to the minus 1 with the inverse mapping. Yeah? So we can go backwards and forwards from automorphisms of the disks to automorphisms of the half space with this mapping. So given, let's say W belonging to the automorphisms of the half space, then if we do this, if we, shall we do, let's do automorphisms of the disk. W automorphism of the disk at phi. Then W of Z, which is equal to phi of f of Z, is an automorphism of the half space, right? So these spaces are these groups are exactly this isomorphic, right? Because we can use backwards and forwards for every single element with this transformation. Yeah? And then using our explicit characterization, it's some algebra. So after some algebra, from this explicit characterization, we learn that if we define this mapping f of m of z to be az plus b over cz plus d, where a, b, c, d are real numbers, and the determinant of this matrix a, b, c, d equals 1, then M is an automorphism of the half space. Okay? And again, this is something I'm not going to prove. This is just a kind of rapid showing you where some of this stuff goes. So what does that mean? That means that we're getting a very, very solid handle on what these group of automorphisms actually is, because this thing here, SL, I think it's SL2, i.e. the set of matrices A, B, C, D, where determinant of A, B, C, D equals 1 is a special linear group. This is a specific matrix group. This is a rather natural, rather easy to understand group, right? And it has a group action or composition, and we know that this is a Mobius transform, and when we compose Mobius transforms, then their composition obeys the composition of matrices, right? So we'd like to say that this group of automorphisms of the disk is isomorphic to this group, but it's not quite true, because this thing can't distinguish if we have matrix M or matrix minus M, right? Because if we just have minus all of these numbers, then we can just factor them out. So since f of m equals f of minus m, we don't have that this group is isomorphic to the group of automorphisms. However, after we mod out this thing, then that's actually true. And that's actually true. So this is called, I think, projective linear groups, or PSL, I think. Is when we mod out m and minus m. I don't know how to write this. Is isomorphic. Okay, so this is really strong, because a priori the automorphisms of the disk could be this huge class of mappings which do many weird and different things. And what this result says is that you can entirely understand them as this group. So this thing, which is an analytic object containing this huge number of potential mappings, all acting on each other as a group, reduces down basically to this thing after we mod out m and minus m. Yeah, this is a very simple group. This is a rather simple, natural, straightforward thing to understand. Yeah? So it's very powerful that we can turn this into this. And it follows from being able to characterize these automorphisms, which follows itself from Schwarz's inequality. And it's a little hint of the connection between group theory and this subject, that you can understand classes of mappings by considering them as groups and then trying to understand better what that group is. And conversely, you can find examples you can study examples of very strange and important groups through complex analysis. So if you read wider into this subject, you'll see that this thing starts to connect with topics such as the monster group, because you can formulate these groups through the subject and do this kind of backwards and forwards analysis through it. So this subject-object analysis connects to many things that you wouldn't necessarily expect. This connects to what is a subset of algebra, right? Which is pretty weird. So we've had connections to partial differential equations, connections to number theory, and this is connections to group theory. So these are very specific functions, very narrow class of functions, but they somehow get everywhere. They somehow spread around mathematics in a surprising way. And that's it, I think, for this class. So please get your homework in. If you have any questions, ask me. I have office hour, but just ask me. There aren't many of you. And keep reviewing for the final. And have a good summer break. All right, bye bye, people.